All right, so here are the solutions to L'Hopital's rule day 2 on pages 423 and 424. So you can go ahead and pause the video because this page I just have the answers. On the following pages I have every problem worked out and I will go over each one. All right, so let's take a look. As we were first trying our direct substitution step, we still either encountered the indeterminate forms of 0 over 0 or infinity over infinity plus or minus. So let's just take a look at each of these as I explain them here. All right, so for number 4, if we try to look at this, it's x is increasing without bounds. So as soon as we substituted in any very large number here, we would get infinity over infinity. So we first start by taking the derivative of the numerator and denominator, but we still encounter another indeterminate form at the second step. So we take the derivative again of the numerator and denominator one more time. This leaves us just with the constant, so 10/14, and simplest form is 5/7. All right, for 9 and 10, they had you completing the table here. So I like this setup because it shows the x values for you, so it made it a little bit easier. But as we take a look at all of our values of f of x here, it starts off a little over 1, and then it drastically decreases. And then if you notice, there's more zeros showing up here. So this tells me that the limit as x keeps increasing without bound. Look at these x values. We have 10, 100, 1,000, 10,000, and 100,000 here that we're looking at. But it seems to be that f of x is getting smaller and smaller, which tells us that it's approaching 0. Algebraically, as we go through this using L'Hopital's rule, very carefully here, taking the derivative of the numerator, we have 1 over x to the 5th times 5x to the 4th, and then we divide that by 1. And then simplifying that numerator, we just get 5 over x. Now we could think of this, we're not going to get an indeterminate form like infinity over infinity. We get 5 over a very, very large positive number, which is practically 0. Likewise for 10, they give us the values here. We're just approaching, x is approaching 0 from the right only. So if you notice, these values were at 1, 1/10, 1/100th, and so on. So typing in carefully these values here, we're getting a 0.1585, and then shortly after, we kind of see this converging or approaching something real quick. So it turns out to be 1.6 repeating, which is actually the fraction 1/6. So if you didn't have the number 1/6, that's fine. We could just leave it as this decimal. But then check when you do this algebraically, divide 1 by 6 on your calculator, you should get 0.16 with that 6 repeating. So algebraically, again, this is 0 from the right. If we substitute this 0 in, we're getting 0 over 0. So we take the derivative of the numerator and denominator once, still substituting in 0 here, we would get 0 over 0 again. So we do that process one more time. And then we're getting sine of 0, still 0 over 0. So we have to do this one more time. Finally, cosine of 0 is 1, and then we have that constant 6. So 1/6 is that 0.16 with the 6 repeating. All right, for 16, no table necessary here, but if we did substitute in a pi over 2, we would get 1 minus 1 in the numerator, and then 1 plus 2 times pi over 2 would give us just pi, cosine of pi, which is -1. So in the very first substitution step, we're getting 0 over 0. So we use L'Hopital's rule. Looks like once here, carefully taking the derivative of numerator and denominator. Make sure you use the chain rule here. So derivative of cosine 2 pi becomes a negative sine of 2 pi times 2. So I just wrote that -2 out in front. We have to take the derivative one more time because we're still facing a 0 over 0, because sine of pi, 2 times pi over 2, will give us pi here. So we still get that indeterminate form. Take the derivative once more, we'll get a positive sine theta up top. Sine of 2 theta, the derivative of that will be cosine 2 theta times 2. So that extra 2 got multiplied by the -2, so I'm getting a -4 out in front. Now when I go to substitute in pi over 2, sine of pi over 2 is 1. Cosine of 2 times pi over 2 is cosine of pi. -1 times -4 here gives us a positive 1/4. All right, looking at 18, we have the limit as t approaches 1 of t minus 1 over the natural log of t minus sine of pi t. Keep in mind this pi t is in its own quantity here. So we would get 0 over 0 at first substitution, so we take the derivative. Carefully, this becomes just a 1 over t minus, this will be cosine of pi times t times pi. So again, we're looking at this as a quantity here, but that pi I'm writing out in front. Now we could try direct substitution. So we're going to get a 1. 1 over 1 is just 1. Cosine, this becomes cosine of pi, which is negative 1. So I have negative pi times cosine of pi. So in the step below that, we have 1 over 1 minus pi times negative 1, which becomes 1 over 1 plus pi. So hopefully you guys were doing okay with those. Some of these later on, there's a little trick, again, because we don't see a fraction, just one fraction here. So 21, we're not there yet. We still just take the derivative of the numerator and denominator, because again, if we were to substitute in 0, not that we would get 0 over 0, but our denominator is still undefined at this point. We can't take the natural log of 0 or a negative number. It doesn't exist. So that's one indeterminate form as well, not necessarily 0 over 0. All right, so taking the derivative of the numerator, we get 1 over y squared plus 2y times the derivative of that function there, so 2y plus 2. Derivative of our denominator is just 1 over y. But I'm going to clean this up, because to take the derivatives again, we definitely want to do something to make it a little bit easier. So I'm going to multiply top and bottom by y. In doing so, I just distributed the y to the 2y plus 2. This whole denominator just becomes a 1. So then I get 2y squared plus 2y over y squared plus 2y. I factored out a y. Now I get 2y plus 2 over y plus 2. Now I can do direct substitution. Even though this is 0 from the right, we can still treat it as a 0. I get 2 over 2, which is 1. All right, 22, 23, and I believe 24. These all had to be manipulated at first before we could apply L'Hopital's rule. Notice in 22, we don't have one fraction here. We don't have a single function divided by another. So the trick here is to rewrite tangent y as sine y over cosine y. Doing that, now we see one function. Even though in the numerator we have to use the product rule when we go to take the derivative. So let's go ahead and do that, because right now we would still get 0 over 0. All right, so looking at the derivative of the numerator, product rule applies. So uv prime becomes pi over 2 minus y times cosine y plus v, which is sine y, times u prime. So pi over 2 is just a constant, minus or times that negative 1. Derivative of cosine y is just negative sine y. Now we could try direct substitution. Pi over 2 minus pi over 2 is this first 0 right here. Cosine of pi over 2 is this 0 right here. Sine of pi over 2 is 1, and then we have this negative 1 here. Sine of pi over 2 is, should just be a positive 1 inside here. I think I was getting ahead of myself with the negative signs. So sine of pi over 2 is just 1, but then we have that negative 1 there. So we end up with negative 1 divided by negative 1, which is positive 1. All right, 23. Again, we need to rewrite this function right here because it's not as a fraction. So rather than multiplying it by x, we can divide it by the reciprocal, because remember, multiplying by a number is the same as, or dividing by a number is the same as multiplying it by its reciprocal. So I just reversed the process here. So just ask yourself, if I were to take this part right here, notice how I wrote it as divided by 1 over x, because if I were to try to clean this up, my next step would be to multiply top and bottom by x, which would take me back to here. So I just reversed the process. We're used to going from a complex fraction into something simpler, but now we had to take that simpler piece and rewrite it as a complex fraction. So I hope you take your time to really look at this part here. So now taking the derivative of the natural log of x, because if we substitute it in the 0, we definitely have undefined in that denominator here. So natural log of x, its derivative is 1 over x. Keep in mind, the derivative of 1 over x is the same as x to the negative first. The derivative of this becomes negative 1 times x to the negative second. So I just wrote this down here like that. But now I want to just multiply, or I could take this whole term up to the top because it is a negative exponent. So this now becomes 1 over x times negative x squared, leaving me with just negative x. And then the limit just becomes 0 here as we substitute in that 0. All right, 24 had a very similar process, but like 23, we could take this tangent of 1 over x. I just wrote it as tangent of x to the negative first, and instead of multiplying it by x, I'm dividing it by 1 over x. So as soon as I take the derivative of the numerator, this will become secant square of x to the negative first times the derivative of this part right here. Like in the last problem, we get negative x to the negative second. Likewise, in our denominator, it's still x to the negative first, or 1 over x. Again, I get negative x to the negative second. So I want to clean this up, so I'm going to multiply by the reciprocal here, negative 1 over x to the negative second. So because this is all being multiplied, what's happening here is when I multiply the numerator by this, these two just turn into a 1, likewise down here. So I'm just left with secant square of 1 over x. Well, now this is giving me, as x keeps increasing without bound, 1 over x is turning into 0, 1 over a very large positive number. So let's take a look off to the side here. That's really secant of 0 squared. Remember, secant square of 0 is the same as writing secant of 0 squared. Well, secant is the reciprocal of cosine. So this is also like looking at 1 over cosine 0, which is 1 over 1 squared. So that just gives me 1. Last two were a little easier. We didn't have to manipulate the original function here. So this is just the limit. It doesn't matter. We're looking at both as x increases and decreases without bound. Again, we would be left with an indeterminate form of infinity over infinity, or negative infinity over negative infinity. So take the derivative of the numerator and denominator. We get 3 and then over 4x minus 1. Now we could substitute in a very large number. So this becomes 3 over either a very large positive number or 3 over a very large negative number. Either way, we're approaching 0. And then 32, much simpler here. Again, we would just be left with 0 over 0 first. So we take the derivative carefully of sine of 7x. This becomes cosine of 7x times 7. Likewise, with the tangent of 11x, it becomes secant square of 11x times 11. Now we could do direct substitution. Cosine of 0 here is just 1, so we get a 7 in the numerator. And just as we went over in number 24, secant square of 0 is the same as secant 0 squared, which is just 1, so we get 7/11. All right, so I'm not giving any new lesson today. I want you guys to take your time to go back over these problems if necessary. Make sure you really look at each one. Continue with the free response question, just so we don't lose some valuable practice time. Over the next couple days, I'll probably just post 1 or 2 more free response questions. After spring break, I usually give a take-home practice AP exam over spring break, but I'll probably just post a couple more, 1 or 2 more free response questions when we get back from break, so you guys can really relax over spring break. What I will also post is scan in some additional kind of like my flashcards papers that I was handwriting out for you guys. I'll post those this week as well, so you can just have some valuable information to help you prepare, along with some more information from the AP College Board. So as always, guys, stay safe. Let me know if you have any questions.